everyone, my name is Dara Patel and I will be doing a practice problem based on topics covered in quiz 2. So, filtration devices act as separators because they have selectively permeable membranes. What this means is that when a substance has a smaller molecular weight cutoff, or MWCO, than the filter, it will pass through the filter with no problem. Now, substances who have a greater molecular weight, however, will not pass through the membrane. So, let's consider a filter that has a MWCO of 3 times 10 to the 5th Daltons that runs continuously to treat a solution that has a mix of superparamagnetic iron oxide particles, or SPIOs, and blood cells, both of which are suspended in plasma. The molecular weight of SPIOs are 1.48 times 10 to the 3rd Daltons, and the molecular weight of a blood cell, let us assume for simplicity's sake that they're all the same type of cell, is 4.5 times 10 to the 5th Daltons. When the stream enters the filter, there is a 2-to-1 ratio of the mole fractions of SPIOs to blood cells, while the solutions contain 85% plasma by mass. This mixture, also please note that there's a difference in mole fractions and masses, so we'll have to deal with that when the time comes. This mixture enters the filter at 7.5 grams per hour. After the stream is subjected to the filter, 2 streams come out. A filtrate stream, which has substances that have passed through the filter, and retentate, which has substances that have not. The filtrate in this particular process is 68% plasma, and the retentate has a flow rate of 4.6 grams per hour exiting the filtration device. Please note that 1 Dalton equals to 1 gram per mole. So for part A, what we have to do is we have to create a community sanction diagram of this process. So let's go ahead and do that. So we know that this problem is based off of a separator. So let's draw our separator. So we know that we have 1 stream coming in, which is our stream A, let's call that. And then 2 streams coming out, stream B and stream C. So our stream A is our mixture. Our stream B is going to be our filtrate. And let's say that our stream C is our retentate stream. So we know that for stream A, we have 85% plasma, so we can say that it's 0.85 plasma. And then we will have some P amount of SPIO, and then some Q amount of blood cells. Because remember, we know the mole fractions, but we don't know the mass fractions, and we can't just combine the 2 of them. Similarly, for stream B, also we know that stream A is 7.5 grams per hour. Similarly, we know that for stream B, we have 0.68% plasma. And since the only other substance in this stream is going to be the SPIO, we automatically know that it's 0.32 mole fraction SPIO. Finally, for the retentate, we have a flow rate of 4.6 grams per hour. And then we also have some X amount of plasma, some Y amount of SPIO, and then some Z amount of blood cells. So before I forget, we have to draw our boundary. Don't forget the boundary. Because that's where our system's boundary is happening, and that's where our system is going to be occurring. So that's what we're going to focus on, of course. The first thing we should do is write out our governing equation, which actually, let's do this in a different color. Accumulation is equal to in minus out plus generated minus conserved. So of course we have no reaction, so we don't have anything generated or conserved. As well, since this is a steady state reaction, we know that our accumulation is therefore equal to 0. So after all is said and done, we have 0 is equal to in minus out, or in is equal to out. The next thing that we're going to do is to do our degrees of freedom. So, degrees of freedom. We know that we have to count out our unknowns, our mass balance equations, independent mass balance equations, our mass fractions, our mole fractions, and then our flow rates. Sorry. FR, flow rates. And that will give us how many degrees of freedom we have. So how many unknowns do we have? We have 8 unknowns because we have 1, 2, 3, 4, 5, 6, 7, 8 unknowns. And then we have 3 mass balance equations because we have 3 different species. Sorry about that. And then we have 2 different mass fractions that are given to us. 1 and then 2. And then we calculated this from this, so we can't count that. And then we have 1 mole fraction because we know that there's a 2-to-1 ratio. And finally, And then finally, we are given 2 different flow rates. So that's 2. So we have 8 minus 3 plus 2 plus 1 plus 2. So that's 8 minus 7, or 8 minus 8. So that's 0. So we're perfectly fine. We don't even need a basis because our basis is going to be the 7.5 grams per hour that were given to us. So let's write our mass balance equations. So we have mass balance equations. So we know that we have 3 different things that we're looking at. We have plasma, we have our SPIOs, and then we have our blood cells. And remember that the basis is that A is equal to 7.5 grams per hour. Now, so we can write our mass balance equations using this information as well as our chart, which unfortunately I can't put in one page because I don't know how to yet. I'm so sorry about that. So we can write for our mass balance equations, we have 85% plasma, so that's 0.85 times A, which is 7.5 grams per hour. And that's our input, right? So that's going to equal to our output, which is going to equal to X, which is what we called the amount of plasma in part C, X times 4.6, which is the flow rate, plus 0.68, which is the mass fraction, times B, which is the flow rate of stream B, which is the filtrate. Similarly, we can say that P times 7.5 is equal to 0.32 B, plus Y times 4.6. Finally, we know that Q times 7.5 is equal to Z times 4.6. Because there's plus 0 technically. There's no blood cells in stream B because it doesn't pass through the filtrate, so we won't count that. And our overall governing equation is that A is equal to B plus C. Now, in order to find P and Q, we cannot just substitute in the mole fractions because they're mole fractions and we're doing a mass balance equation over here rather than a mole balance equation. So in order to find P and Q, we're going to have to convert the moles to mass. So in order to do so, let us assume that we have 100 grams of mixture. Now, if we have 100 grams of mixture, knowing what we do about the properties of the mixture, we can say that there's going to be 85 grams of plasma. And then, of course, 100 minus 85, which is 15 grams of SPIOs plus blood cells. The question here is, though, what is the ratio within these 15 grams? And that's what we're going to be trying to find. Now, we know that the number of moles of SPIOs times the molar mass of SPIOs, or the molecular weight, which is 1.4 E3 daltons, plus the number of moles of blood cells times the molecular weight of blood cells, which is 4.5 times 10 to the 5th daltons, plus 85, which is the number of grams of plasma, is going to equal to our total, which is 100 grams of mixture. Now, in order to find out how much SPIO, or how much blood we have, this is where our use of our mole fraction comes in. So we know that Y of SPIO, which is our mole fraction, over the Y of blood is 2 to 1. So, using this property, we can safely say, or like this fact really, we can safely say that 2 times N of blood times 1.48 E3 plus N of blood times 4.5 E5 is equal to 15. Therefore, we know that our N of blood is equal to 3.312 E negative 5. So that's how many moles of blood we have. Okay, sorry. I tried to erase that, clicked on the wrong thing. Moles. Okay. Now, in order to get the mass of our SPIO from this, we can say that 2 times 3.312 e negative 5 times 1.48 e3 is equal to our mass, which is equal to 0.098 grams. And now if you divide this by the total number of grams, which is 100 grams, you will get 9.8 e negative 4, which is equal to our mass fraction, which is P. So that means that is P. Similarly, we can say that the mass of blood is equal to 3.312 e negative 5 times 1.48 e3. Oh, whoa, sorry, I'm so sorry. Not that. My bad. Let me just fix that a little bit. Sorry about that. Sorry, 3.312 e negative 5 times 4.5 e5, because that's the molecular weight of the blood cells. And that's equal to 14.904 grams, which divided by 100 grams is equal to 0.149, which is our Q. So now that we know P and Q, we can substitute both of these values back into our equations, which makes doing the equations a lot simpler. So let's see if I can maybe transfer this. Oh, okay. So let's move that a little bit. We have these as our mass balance equations, and we also know now that P is equal to 9.8 e negative 4, and also that Q is equal to 0.149. So let's substitute these values in for our equations. We can say that for plasma, actually, let's do this. Let's do this in blue. Plasma, 0.85 of 7.5 plus, sorry, no, not plus, I'm so sorry, equals X times 4.6 plus 0.68 times B. Then we can say that for the SPIOs, 9.8 e negative 4 times 7.5 is equal to 0.32b plus y of 4.6. And then for our blood cells, we can say that 0.149 of 7.5 is equal to z times 4.6. Now we have too many variables at this point because we have our x, y, and z, and then we also have b. So in order to reduce the number of variables, we have to reduce it down to 3 because we only have 3 equations. So we can say that z is equal to 1 minus x plus y. So let's go ahead and do that. So 1 minus x plus y times 4.6, which is our blood equation in a simplified form. Well, not simplified, I guess, in a changed form. And then 0.149 times 7.5 is equal to 1.1175, which is equal to 4.6 minus 4.6x minus 4.6y. Similarly, we can say that 9.8 e negative 4 times 7.5 is equal to 0.00735, and that's equal to 0.32b plus 4.6y. And then we can say that 0.85 times 7.5 is equal to 6.375, which is then equal to 4.6x plus 0.68b. Now, in order to do this, we can plug everything into the calculator, or we can do it by hand. Of course, we can use matrices, or we can just do substitution and systems of equations. So I'm going to go ahead and just try to do substitution. So let's say that 4.6 x is equal to 1.1175 minus 4.6, which is negative 3.4825 plus 4.6y. Sorry, I had to add that negative sign. So in order to say that 4.6x is positive, let's make the 3.4825 positive as well as the 4.6y. Or sorry, the 4.6y won't be positive, my bad. So we can substitute this equation right back into the top one, and then say that let's see how to figure this out. 6.375 is equal to 3.4825 minus 4.6y plus 0.68b. And then we also know that 6.375 minus 3.4825 is equal to 4.8925. So let's go ahead and substitute those values. So 2.8925 is equal to negative 4.6y plus 0.68b. And then we also know that 0.00735 is equal to 0.32b plus 4.6y. So if we simply add these two equations, we can eliminate y, and we can say that b is equal to 2.8925 plus 0.00735, which is 2.899, not 3 nines, my bad, 95. And because we know what b is equal to, we can now say that we can find out what y is equal to. So we can also say that 2.8925 minus 0.68b is equal to 6.921. So that divided by negative 4.6 gives us our y, which is negative 0.2001. Now, of course, I know that technically you can't have negative mole fractions because that's not possible, but because I just devised these problems to really show you how to do it, and I'm not a textbook editor, I haven't really been able to verify the values. So I'm basically showing you this for more the process than I am for the actual values. So these aren't the real values. You will never have a negative mole fraction. But for the purpose of this problem, let's assume that we can have a negative mole fraction in real life using warped laws of physics and nature. So if we know that our y is negative 0.2001, we then know that our x is 3.4825 minus 4.6 into negative 0.2001. So our x is, and then divided by 4.6, sorry. So x is 0.9572. So now we have all these variables that we've solved for, but we have to figure out what the question is asking. So what's the question asking? Let's go back to the question. So our question is asking us what the mass fraction of the SPIO in the filtrate is, and then what the mass fraction of the blood cells in the retentate is. So the mass fraction of SPIs in the filtrate is going to be 0.32. So I didn't realize I accidentally wrote mass instead of mole. So let's actually alter this question a little bit and say, instead of mass fraction of the SPIO in the filtrate, what is the mass fraction of, actually let's just do mass. So let's just say, what is the mass of SPIO in the filtrate? So then we can say that what we're solving for right there is simply 0.32b. Oh, sorry. I didn't even know you could do that. So our answer for part B will be 0.32b. So that's our number one, or sorry, our A. Or sorry, B, my bad, because A was the diagram. And then we want to know our mass fraction of the blood cells in the retentate, which is the same as Z. And then D is our flow rate of the filtrate, which is just B. So let's go ahead and apply our variables in order to solve these equations. Sorry. Trying to figure it out. Okay, so these are the things that we're solving for. If we go back to our previous page, we know that, oh, my bad. If we go to the next page, which is where all our equations are, we know that our B, so let's just copy all this actually. All right, let's see if we can paste that. Oh, that is not what I wanted. Okay, maybe not. Anyway, that's okay. We'll just rewrite it. We know that our B is 2.8995. So B is equal to 2.89995. And then our Z can be solved by saying that 1 minus y plus x is equal to z. So our y is negative 0.2001, and then our x is 0.9572. So we can use that to solve for z. So y is equal to negative 0.2001, and then our x is equal to 0.9572. So we would be 0.32 times 2.89995. So that is simply 0.9279. So C is going to be our Z, which is going to be 1 minus negative 0.2001 plus 0.9572. So what is 1 minus those two? Negative 0.2001 plus 0.9572. So our Z is going to equal to 0.2429. And then for our D, which is simply our B, so that's going to be 2.8995. Now we have to add our units, and we have to know, or make sure our sig figs are right before we finish off this problem. So we're only given of a minimum of 2 sig figs within our problem based off of all the numbers that we're given. So we know that we need 2 sig figs for all of our responses. So that's going to equal to 0.93. That's going to equal to 0.24. And that's going to equal to 2.9. And our units. So this is a mass fraction. So this will be unitless. This is a mass. So this is going to be in grams. And then this is our flow rate. So it's going to be in grams per hour. And this ultimately is the answer to the problem. And I really hope you learn how to do it properly. And I hope this video tutorial was helpful for you guys. So thank you so much, and I will see you guys later.